Hey everybody, we're continuing our discussion about Chapter 5, which is stereochemistry, and right now we're kind of in the middle of the chapter discussing optical rotation. It's kind of a physical method we can use to observe chirality in molecules, and it has to do with the rotation of light. And we have a figure from the PowerPoint that I'll review real quickly. So this showed, we discussed this last time and we went through what was going on. This is one of the figures in the PowerPoint. It's in the textbook also. But the idea is that you start with light, just normal light. It's usually a single wavelength from a sodium lamp or something. And then the light is oscillating in all planes, all directions, and the idea is we apply a polarizing filter, which lets us filter out all wavelengths except, all planes of light except one plane. So it's a single plane of light, right? And then you have this plane polarized light transitioning through your sample, and then for some crazy physical reason the light gets rotated. The exact physics behind that is a little uncertain. I don't know what the consensus is, but what you need to know is that the plane gets plane polarized light rotates either in the positive direction or the negative direction, and there's no way to look at the molecule and figure out, like, is it going to go positive or negative. That's a very critical thing. We can't look at this and be like, oh, based on the structure, oh, it's going to go negative. Indeed, it did go negative here. We don't know that, or we don't have a way of knowing that, right? Okay, so then you basically just use a different filter at the end, and you rotate that, and you figure out an angle. So the net result is that you get an angle out. It's called the angle of rotation, right? Or alpha. We call it alpha. Okay, we also mentioned that once you have the alpha value, it's also called the observed rotation. You can do this normalization thing. It's called bracket, alpha bracket, or specific rotation. And this is just a way of normalizing the alpha value based on the length of the sample tube, and it's usually 1 decimeter, and the concentration. So path length and grams per mil. You don't have to do this calculation in the quiz or anything, so don't worry about that. D means the sodium emission line, or it's called the D line, which is just 589 nanometers, and then 25 degrees is the temperature. So these variables are usually specified also. And last time we mentioned a couple examples of this. So 2-bromobutane, there's 2 enantiomers of it, right? And there's the one where the bromine's going away and the one where the bromine's coming towards you. And they have different standard rotations. So negative 23.1 would correspond to this molecule, and it's called negative 2-bromobutane. Negative 2-bromobutane. The negative here refers to the negative there, right? Okay, then we have the positive version, 23.1. This molecule is called alanine. It's one of the amino acids because it's got an amine and a carboxylic acid. It's got a CH3, it's going away. There's also an H that's coming towards us. We're just not showing that. But that's 8.5. And this is positive, so that's positive. Positive alanine, okay? We mentioned carvone. Carvone is one of those things that has a 6-member ring, alkene, ketone, and then this thing is a 3-carbon piece that's coming towards us with an alkene. What's an alkene? It's the double bond, right? Anyway, so this is positive 61, and the molecule is called D plus carvone. D and plus are redundant because D means plus, right? It's dextro rotatory. So D and plus are redundant, And this is the one that smells like caraway, and if you do the Enantiomer, it smells like spearmint. It's a really fun thing to do in the lab, or when I teach the class in person, we pass around a vial that shows those. So the Enantiomer is a -61, and it's L minus carbone, and it's the one that smells like spearmint. Okay, and in this case, the 3 carbon piece is going away from us, and the H is coming towards us. But you can see the mirror relationship, but I forgot the ketone. Whoops, alright, didn't see that last time, but yeah, I missed the ketone. Okay, and what about like something that is achiral, like chloroform, which could be a solvent to dissolve your sample. Chloroform, CHCl3, it's achiral, of course it's going to be a 0 rotation. Ethanol, same thing. Ethanol is an achiral solvent, and we often, when we do these experiments, we often like dissolve this stuff in ethanol or chloroform, and we use these solvents because they are inert and don't rotate, right? And ethanol rotates at 0. Okay, so a little more on optical rotation and optical activity. So we're on number 2, optical activity. Number 2, optical activity. And so let's talk about that bromination reaction one more time. Consider again bromination. Of butane. So we'll show butane, and we'll do the Br2 reaction, heat or light. And we already kind of showed, sort of mechanistically, you know, what happens. Of course, you have Br dot, rips off the hydrogen. Let's skip the arrows and just get to the intermediate. So we actually have 2 hydrogens, right? There's 2 hydrogens. We rip off one of the hydrogens, and you're left with the other hydrogen. And it's a radical. Secondary radical, and remember, of course, this can happen to either put bromines on the ends, primary bromination, or in the middle, which is secondary bromination. So we're just going to show the secondary bromination, and in the end, there's basically 2 products, right? And those are 2-bromobutane. 2-bromobutane, 2-bromobutane. If I, and of course the mechanism, I'm going to skip the mechanism, but you know, this is prop 1, this is prop 2, right? Prop 1, the Br rips off the hydrogen. Prop 2, the radical attacks Br, and you get your product, and Br dot, right? Okay, so, but you make this mixture of products, right? And what's the relationship of those 2 products? Are they the same molecule or not? What's the word? It's begins with the letter E. These are enantiomers, right? So those are enantiomers. What are the what is the specific rotation of those 2? We just got that from the little chart. The specific rotation, which is the alpha, the bracket alpha value. Well, one is -23.1. The other is 23.1. Okay, and right, and the one of them cancels the other. So the net result is the end product is a mixture of these 2, right? And they cancel each other. What's the name of that? It begins with R. It's the name of when you have a 1-to-1 mixture of 2 enantiomers. Enantiomer, enantiomer. The 1-to-1 mixture of the 2 enantiomers is called the 50-50 mixture of enantiomers. The 50-50 mixture of enantiomers is called a racemic mixture. right? Okay, so, and now we know that of course it makes sense. You know, there's no preference for the radical attacking with the, you know, for the BR to wind up on the front, or radical attacks so the BR winds up in the back. There's no preference for one way or the other. That's why you get a one-to-one mixture. And now we know the rotation of those two things, and it makes sense that if you have a pair of enantiomers that are forming at equal rates, that you would get a racemic mixture. Okay? All right. So, and also, if they cancel out, it's called optically inactive, right? It's optically inactive. So the rotation, the net rotation is what? The observed rotation and the specific rotation is 0, right? Because they cancel each other out. And that's called optically inactive. Optically inactive, okay? All right, cool. So, and then it's interesting to consider, you know, like if you have optical inactivity, or you have something that's optically inactive, there's two situations usually. Optically inactive. So if you observe a 0, like equals 0, and you have an optically inactive mixture that's not rotating light because you have a 0 rotation, 0-degree rotation. What are the two reasons for that? There's two reasons for your sample being optically inactive. One, you got an achiral molecule. It's just not chiral, right? If you got something that's not chiral and you measure the optical rotation, well, of course it's going to be 0 and it's going to be optically inactive, right? What's the other situation where you have optical inactivity? Optical inactivity. It's what we got up here. Now it is chiral, but you have a racemic mixture, and the racemic mixture cancels each other out, and so, and then you have a it's optically inactive, and you have a observed and specific rotation of 0. Okay, and that's optically inactive. So the second situation for optically inactive is that it's achiral, it's chiral but racemic. Chiral but racemic. Okay, so optical inactivity is due to achiral or chiral but racemic. The book, so if you're following along in the book, it discusses a concept called Enantiomeric Excess. And we are skipping it. Okay, all it is though, when the book discusses an enantiomeric excess, it just kind of means like, what if you have like maybe 10% more of one enantiomer versus the other, or something, or like not, and it's, you know, not like a pure enantiomer, but maybe a slight mixture, and that's called enantiomeric excess, and we're not going to get into that, so you can skip that. If you see it, just skip over it in the book, or you can read about it. Won't see it in this course anymore. Alright, moving on. We talked about optical rotation and optical activity. Let's talk now about something called, we'll give it a number, 3, absolute configuration. Absolute configuration. Absolute configuration of chiral molecules. absolute configuration of chiral molecules, all right? And I'm going to put a little squiggly because this is not a huge thing in our discussion. I'm just going to bring it up. So when we talk about rotation, specific rotation, does alpha, specific rotation, does alpha tell us anything about the three-dimensional structure of the molecule? Well, that's a question. Does alpha tell us anything about the three-dimensional structure of the molecule? So we know, for example, that like this molecule, this 2-bromobutane is rotates light at negative 23.1 degrees, and the enantiomer rotates light at 23.1. So you might say, well, I mean, or maybe the question is, does alpha tell us anything about the three-dimensional structure? Like, if I look at that number, negative 23.1, can I be like, well, oh yeah, somehow maybe that correlates to the structure and it causes the rotation of light to be negative, right? And that this one somehow causes it to be positive. Well, that is not known. That is not to my knowledge, and I'm pretty sure that through physics and understanding of optics, we've never been able to do that. So this is not like the question is like, yeah, are these like correlatable, right? Can I correlate the sign to the structure or the structure to the sign, right? The answer is no. So let's say no, x, no. You can't do that. You cannot correlate the structure to the sign or the sign to the structure. Okay. All right. So how do we know that? Like, how do we know that this sign correlates to that at all? The way is because through other methods we figure out the structure of this. We like can determine the chemical structure of this, and we've done this probably 50 years ago. If we know the structure of it and we know this, then we can make the correlation. But I can't like take an unknown molecule and look at the structure and then figure out the sign of the optical rotation. Okay, so if that makes any sense. Like, we can make this, and there's ways to isolate this and determine its structure independent of optical rotation. And then, if we know it with absolute certainty, and we take the optical rotation, and it's negative 23.1, then now we know that this structure correlates. But there's no way to just look at the structure and say, oh, it's negative, or that one, and oh, it's positive, okay? So, that's just a subtle point, right? You might think we could, but we can't. We can't easily correlate the structure with the sign of the rotation. Okay, so I'll write that out in words. And the question was, does alpha tell us anything about the 3D structure? The answer is no. Alpha is a physical constant. About light rotation. Okay, and it doesn't correlate directly to the structure. It does not correlate to chemical structure. Okay. Okay. If you isolate a molecule, now this is a known molecule, but what if you isolate an unknown molecule? If you isolate an unknown molecule and you want to figure out its three-dimensional structure, like is it a wedge or a dash, right? If you have an unknown molecule and you want to figure out this structure, that is actually a very difficult thing. It's not just stick it in the polarimeter and you know, see the rotation. So if you have an unknown molecule with a chiral center and you want to figure out is it a wedge or a dashes, that is actually a little challenging. And I'm just going to mention the technique that we would use. So the technique we'd use for that is called X-ray crystal diffraction. This is the main method. There's a couple other methods, but this is a very, very complicated technique. I call it a black box technique that we can't really discuss because it's a very complicated. The main idea, though, is like if you grow crystals of a substance, you crystallize it, right? You can shoot X-rays at it, and then use computers and you know, to examine the diffraction patterns. You know, how the X-rays diffract on the crystals, and that can be used to kind of figure out the 3D structure. So that will give you the 3D structure. Okay. Side note, if you like proteins, right? Proteins are very, very complicated molecules. And you've probably in your biology classes seen 3D structures of proteins, right? You could probably Google it. 3D protein X-ray crystallography. Or yeah, X-ray crystallography is another name for this. X-ray crystallography. So this is a technique where we use X-rays and crystals to basically figure out the 3D structure of things, whether it's a very simple molecule or a crazy protein with like 10,000 atoms. And this will tell you the coordinates of every atom in the molecule, or, you know, big protein, DNA, whatever. Okay, so there's a lot to this. We're not really going to get into it though. Okay, that's why I put the little squiggly up there. This is not really a testable topic. I just wanted to mention, how do we figure out the absolute configuration of a chiral molecule? The main answer is X-ray crystallography, or you can say X-ray crystal diffraction, which basically mean the same thing. There's also on my little handouts just a little clip from the Wikipedia page of X-ray crystal diffraction, so you can take a look at that. It's got a paragraph of text on this. It is like I said, a very complicated technique, or what we call black box technique, which is just like you would become a specialist in this very specific technique, and then you can do this and solve protein crystal structures, or, you know, the crystal structure of a small molecule, like you know, in the realm of something like this. Okay, all right. So that's X-ray crystal diffraction. One other little tidbit about this X-ray crystallography, and again, not really dwelling too deep on this, X-ray crystallography implies crystals, right? And the problem we sometimes have is like a molecule like this is actually not a crystal, it's a liquid. And so there's some other tricks you have to do to turn it into something that's crystalline, right? A lot of molecules are crystalline, like a lot of proteins. Proteins are crystal. And so it's easy to crystallize a protein and then get the X-ray crystal structure of it. Well, not necessarily easy, but it's doable, it's possible. You would not be able to crystallize this, so there's other tricks you need to do that. Okay, so now we're on to something that's more important. X-ray crystallography is not really important. You just need to know kind of about it, but it's not something you're really tested on or quizzed on or anything. So number 4, though, is important. This is nomenclature for absolute configuration. Nomenclature for absolute configuration. And this is it's a couple of rules. We call them the CAHN, C-A-H-N, Ingold, Prelog rules. The CAHN, Ingold, Prelog rules, okay? Or you could call them CIP. Ingold Prelog rules. Let's put a star to suggest this is a very, very important thing you gotta totally know inside and out. Maybe abbreviation for this idea is the RNS rules. RNS rules. Because our designation for chiral molecules are either going to be called R or they're going to be called S. Okay? Alright, so let's do an easy example first. And then we're going to transition to more complicated examples. Alright? So let's just first think about, like, how to name this molecule. How do we name this molecule? Okay, so we got a bromine, we got a 4-carbon chain, of course. What's the name of it? What's the name of that? That's, ignoring the chirality, you should have a good name, right? Looks like it's butane with a bromine on number 2, right? 2-bromobutane. All right. Is this a chiral molecule? Yes or no? Yeah, it's chiral. How do you know it's chiral? It's got a chiral center. It's we can put a little star there if we want. Yeah, it's a chiral molecule. And being chiral, it must have a something. It must have a, what's the thing it must have? Kind of a partner. The thing it must have is a En, or enantiomer. I'm going to draw it in the kind of mirror image configuration here. Okay? Alright, so you can kind of see the mirror relationship of these things, how they're mirror images, right? They are mirror images, and they're enantiomers, okay? And of course, remember when I'm drawing an enantiomer, there's another way to draw it, which is kind of take the enantiomer and I flip it over horizontally, take it out, flop it over, then it kind of looks like this, right? But it's different. It's not the same, obviously, because this is not the same as this, nor is this the same as this. These are the same, but Br would be going away, and the hydrogen would be there. All right, so that's the enantiomers. So 2-bromobutane, but these are different molecules. This is also 2-bromobutane. So how do I describe the difference between the two enantiomers? That is this whole topic, nomenclature for absolute configuration in the Ingold Prelog rules. All right, so we need a way to distinguish this through nomenclature, this molecule from this molecule. All right, so we need a way to distinguish those two guys. We need a way to distinguish those two molecules. Alright? Exclamation point. We need a way to distinguish them. Okay, and so it's basically a two-step process. Number one, step one is going to be figure out priorities. I'll explain what that means in a second. Figure out priorities. And I'll show what I mean by that. Figure out priorities. And then once you have the priorities, then you have to do number 2, which is assign RRS. Okay. I should also mention, I'm explaining this slightly different than the book. It gets you to the same point. I just think my method's a little cooler than the book. So you can always just read the book and get to the same point. But this is my method. This is the Mark method for determining RNS. Right. So we figure out the priorities, and there's kind of like 3 rules for figuring out the priorities. There's three ways to figure out the priorities. First one is atomic number wins. Atomic number wins. Atomic number wins, and we'll see, like Br is a high atomic number. It's, if you look on the periodic table, it's a higher number on the periodic table, so atomic number will win. The other thing we do is we walk away. We walk away until the first point of difference. Okay. Walk away until the first point of difference. I'll explain that in a second. Alright? So far the rules are atomic number wins, and then we walk away until the first point of difference. And then the third rule is going to be double bonds. Double bonds, which we'll see basically mean multiple single bonds. Okay, that's going to be a little bit advanced one, so let's wait on that one, double bonds. We'll first focus on single bonds, and these two rules are pretty easy. Atomic number wins and walk away till the first point of difference. Once you got the priorities, you have to assign R or S, and there's a couple different ways we can do this. Couple different ways. Alright. We'll show you the different ways. All right. So let's do an easy example. Simple example. Will be our 2-bromobutane. This guy up top. Let's redraw it. All right. 2-bromobutane. So the priorities is our first step. Figure out the priorities, right? Figure out the priorities. Figure out the priorities. So the priorities, we already mentioned that the atomic number wins and then walk away until the first point of difference, right? So atomic number wins basically means that we have 4 things on the carbon, right? We have a bromine, we have a hydrogen, and we have a carbon and a carbon. Atomic number, look at the periodic table. You should have a periodic table somewhere, or just know that bromine has a fairly high atomic number. It's the number in terms of going down the counting through the elements, right? Br is a big number, so I call it A. What's H? Is it a big number or a small number? It's a tiny number, right? So is D. It's number 1. It's the lowest atomic number. Okay, so now we're on to the second rule, which is walk away until the first point of difference. Because now we have a carbon, a CH3 or a CH2CH3, right? So if you look at the carbon versus carbon, well, they have the same atomic number. So then we walk away until the first point of difference, and the difference is very clear that that's a CH3. This is a CH2CH3, so this has an extra carbon. So additional carbon will, the extra carbon will win over that. So this becomes B, and this becomes C. Okay, so that's the first thing we have to do. Figure out the priorities, A, B, C, and D. Okay, that was not that hard, I hope. Okay, all right. And then what's the next thing we do? We got to figure out the R or S, and there's a couple different ways. I'm going to show a couple different ways to do this. I'm going to first show the kind of easy way. Can't always use the easy way, but this is a case where the easy way works. So, if the D substituent is going away, then it's really easy. And of course it is going away, right? H is going away. If the D substituent is going away, then we look at A, B, and C, A, B, and C, and they're going clockwise, right? A, B, and C are going clockwise. And that's R. We just did it. That's R. Our answers are R or S. And then the full name of this becomes R2-bromobutane. R in parentheses, 2-bromobutane. That's the final answer. Okay? What if the ABC is not clockwise but counterclockwise? Then it's going to be S. So let's look at the enantiomer, and we know that if this is right, the enantiomer will always be S, right? The enantiomer will always be the opposite. So let's draw the enantiomer and try the same trick. Okay, so the enantiomer, we drew it up here. It's just going to be the ethyls on the left, the methyls on the right. Okay, so let's try out the enantiomer now. Okay, so I'll just draw the enantiomer out the same way we drew it. It really helps for this so far. Okay, so there it is. There's the enantiomer. We think it's going to be S. It probably will be S, but let's check it out and draw out the priorities. What are the priorities? Who's the A? A is the BR, right? Here's the D. H is the D. Who is the C? Well, who's the B? Who's the B? We have B and C left, right? B is going to be on the left. C is going to be on the right. Okay, so we have A, B, C, and D assigned. That's the first trick, or the thing we got to do. Pretty easy. Use atomic number and first point of difference. Now we look at the H is going away, right? This only works if the H is going, if the D is going away. The H is the D substituent, the low priority. So if the D is going away, then we look at A, B, and C, and now we're like, oh, look at that. They are going counterclockwise. And if they're counterclockwise, they will be S. That's it, you know. If you have this situation where H is going away, this is incredibly easy. This works out pretty well. This is S2 bromobutane. S2 bromobutane. Okay? S2 bromobutane. So we have R2 bromobutane and S2 bromobutane. And now we just got to do some more random examples to get you better at this, okay? And like I said, there's a couple ways to determine R and S. This is one method. We'll show another method in a second, okay? Okay, so let's we got this first way of doing this, right? If the D is going away, then you do either clockwise R or counterclockwise S, right? That works really well, but it implies, or it requires that H is going away, like here. These two examples are wonderful because the H is going away. What if H is not going away? Then we have a couple other tricks. I'm going to show you one method that I love, and you may really dislike it first until you get it down, but I just want to introduce it, okay? The thumb method. The thumb method. The thumb method is a mark method. I created this method. I think I haven't really seen other people describe it. It may be out there. But I'm going to sort of take credit for this, the thumb method. Okay, it's great. We have thumbs, and this will allow us to easily figure out R and S. Okay, so the thumb method is we poke our thumb in the direction of the D substituent. Okay, and then we wrap our fingers. We wrap our fingers around in the A, B, C direction. Wrap fingers in the A, B, C direction. A to B to C. Okay. And only one hand will do this correctly. And if it's the right hand, it's R. If it's the left hand, it's S. So that will work every time to figure out R and S, right? Let's try it. It's a little hard with the camcorder. I'm going to see if I can do this. So let's first look at this molecule. We know it's R. We know it's R, right? So what I'm going to do is demonstrate the thumb method with this one. And the way I'm going to do that is I am going to poke my, I hope you can see it, it's getting a little hard to orient, so let's see if I can Let's see if I can do this. Alright. That's R, yeah? So what I'm going to do is use my right hand. You should do this also. We have to poke our thumb in the direction of the D substituent, the lowest priority substituent, which is going into the paper, right? So I'm going to poke my right hand into the paper, and if you look at my fingers, they will wrap from A to B to C. A, B, C, kind of like, right? A, B, C, A, B, C, A, B, C, right? It goes A, B, C, A, B, C, A, B, C. And what do I say about right hand? It's R. Do you see it? You see how I did that? This works every time. So this is an amazing method, especially if the H is pointing in some different way. All right. Let's try my left hand. Let's try the left hand, okay? So on that same left molecule, we know it's R, but let's try the left hand and see, you know, to rule out the left hand. Because if I poke my thumb into the paper and I rotate my fingers, and you can try it, right? ACB. That's wrong. ACB does not work. It has to go ABC, right? Look at the ACB. If I try my left hand, it does not work. So it's not R. I'm sorry, it's not S. Left hand would be S, right? Try my right hand again. It matches ABC, ABC. But the thing about this method, and this is where students kind of get confused, is you always have to have your thumb in the direction of the D substituent. Okay? Let's look at this one. We know it's S. We already determined it's S. This is totally right. It's absolutely S. Okay? So there's no question it's S, right? Let's try my right hand, which would give me R, and we'll see if it works. It shouldn't. Okay? Where's the D substituent? It's going into the paper. So where's my thumb going to go? Into the paper. Try the right hand. And I try my right hand, and I poke my thumb into the paper, and I go ACB. ACB. Oh, that's wrong. It should not go ACB. It should go ABC. Right hand doesn't work. It's not R, right? Let's try the left hand. Thumb goes in. ABC. 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 Ah, it's S, just like we determined before, right? So the thumb method is one way to do this, and it works every time. What was this other method we did? This was the poke the D in the opposite direction of the paper, and then if it's clockwise it's R, and if it's counterclockwise it's S. A lot of people love this method at first, right? But the downfall is that the H has to be in the plane of the paper, otherwise it doesn't work, okay? Alright, so with a couple more examples, this is going to get a little better. Alright, so now we have two methods for number 2, assigning RS. Either this, have D in the plane, and draw R and S, R clockwise, S counterclockwise, or the thumb method. Poke your thumb in the direction of the D substituent, wrap your fingers, ABC, and right hand works R, left hand works S. Alright, so we introduced this idea of nomenclature of the R's and S's, right? It's called the Ingold Prelog method. So it's basically R's and S's. There's more to talk about, but we at least did a good example of it. Let's go back real quickly to this molecule, right? Let's go back to this molecule. Okay, let's go back to this. This is S2-bromobutane. We showed it with the D going in, you know, counterclockwise. We showed it as S, right? We also showed it with the thumb method. So we showed two methods for this molecule. Let's do another. Well, let's take it and flip it over, because we already showed what that looked like. Take it and flop it over, because that is a different situation. Because now the H won't be going in the plane, right? So we drew this. Let's take it and flip it over. It should still be the same molecule. It should still be S2-bromobutane, right? You take it and flip it over, it shouldn't change to R. It would never change to R if we just took it and flipped it over, because R is a different molecule, right? So let's take it and flop it over. All right, so I'm just going to redraw it here. Okay, so there it is. We already gave it a name. It's S2-bromobutane. S2-bromobutane, right? We did that with the thumb method and also the counterclockwise method, which works sometimes. But what if I just flip it over? Flip it. It still should be S, but now it looks like this. So the name should still be S, but let's see if we can confirm that with using our methods. Okay, so pretend we had this, and we're like, oh yeah, let's figure out R and S. Of course, it should be S, but let's pretend we don't know that. What are the priorities? BR is the A. What's the D substituent is maybe the H is D. And who's the B and who's the C? B is going to be the ethyl group. C is going to be the methyl group. Alright? So if you got this and you're like, oh no, is it R or S? There's a couple ways you can proceed. Okay. I'm going to do the thumb method first because I love the thumb method. Alright? Where do I poke my thumb when I do the thumb method? In the direction of the D substituent, right? So H is coming towards us. Where's the D? Where's my thumb going to go? Towards me. Towards me. And now, if I poke my thumb towards me, like the D is going towards us, then with my left hand I go A, B, C. Oh, look at that! Look at that. Left hand, A, B, C. Right? Yeah, it's S. It's S2-bromobutane, right? That just shows the beauty of the thumb method. 2-bromobutane. Of course, these are the same molecule because all I did is I flipped them, right? Now, the common misconception is people just see ABC clockwise and they're like, oh, clockwise R, right? But that's wrong because the clockwise method requires the D to be going away, right? And the D's not going away, the D's coming towards us. So this is where students often mess up. They're like, well, I see clockwise ABC, and I say, oh, it's automatically R. That only works if the H is going away, right? That's the beauty of the thumb method. As long as you poke your thumb in the direction of the D substituent and you wrap your fingers in the direction of the ABC, left hand's S, right hand's R. Let's try my right hand. Shouldn't work. Poke my thumb towards me and I go ACB. Oh, ACB is wrong, right? Thumb up. ACB doesn't work, right? So that just shows the beauty of the thumb method, okay? All right. But I should mention, and this is, if you look at Khan Academy and other websites and stuff, there is another trick you can do, which is this. You can, we know, okay, if H is going away, like H is going away here, and it's A, B, C, right? And this is S, right? A, B, C, D, right? Okay. We know that if H is going away and it's counterclockwise it's S, it's clockwise it's R, right? We know that. So a trick you could do is if and this is one of the tricks people use. I don't necessarily like this, but I'll just mention it. A trick is that if the H is coming towards us, so that then you look at like R, clockwise R, but then you just do the opposite, right? So ABC clockwise it would be R, but since H is coming towards us, R becomes S. So that would be another way to do it. I usually don't teach that, but if you look online, you'll probably see that somewhere. Some YouTube videos, people are going to be like, well, if H is coming towards you, you just do the clockwise R, counterclockwise S rule, but you do the opposite of it, right? So this is clockwise, which would be normally R, clockwise would normally be R, but since H is coming towards us, you just say, well, it's not R, it's S. Okay. All right, so we have a couple different ways we can do this now. Let's do more examples. Let's try another example. Alright, so maybe draw my HN. Okay, so this should be pretty easy. Let's do our ABCs and Ds. So who's the A? Probably think atomic number, right? Chlorine, yeah, high atomic number relative to carbon, yeah, that's A. What about maybe the D? I usually do the A, then the D, and then figure out B and C. So maybe D is the H. It's really easy when when you have an H, it's usually the D. Now we walk away until the first point of difference. So I'm like, okay, well, I got a carbon with 3 carbons on it, or I have a carbon with 1 carbon on it. Carbon with 3 carbons, right? 1, 2, 3, or a carbon with 1 carbon. Who's gonna win? Probably this guy. And then we got C, right? Okay. Thinking about the name of cycloalkanes, the numbering would probably be from the 2 substituent, the 2 methyls to the 1. So it's probably going to be 1, 2. I'm not going to review that. That was in the chapter, the previous chapter. You would number from the carbon with the more substituents. So yeah, so the name is going to be 2-chloro, because you put the chlorine before the methyls. It's going to be 2-chloro, 1, 1 dimethyl cyclohexane. 2-chloro, 1, 1 dimethyl cyclohexane. Now we got to figure out R and S. So let's do the R and S. Alright, so this is a really easy one because D is going away, right? D is going away. It looks like ABC goes counterclockwise. So should be S, right? ABC is counterclockwise S. If you don't believe that, try your thumb. Point your thumb into the page. Point your thumb into the page, and then it goes. Starts at A, B, C. Left hand S. Left hand S. A, B, C. A, B, C. A, B, C. Right? Left hand works. As long as you point your thumb in the page, it always works. But since H is going into the page, you don't even need to use the thumb method. It's really easy. A, B, C, left. Okay, so we try S. Okay, cool. I want to show another method for figuring out R and S. It works in some cases really well. It's the stick figure method. So this is the third method for figuring out R and S. It works if the H is in the plane, or if D, the D substituent, is in the plane of the paper. If the D substituent is in the plane of the paper. The D is in the plane of the paper. So an example is this one. If I say H, here's a carbon, we got a dash 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 iodine, and a wedge Br, and a CH3. Alright, so the trick here, the priorities are easy, right? Here's the A. A is the iodine, right? Because it's got the higher atomic number than bromine, right? B is going to be the Br. Methyl is going to be the C. And the H is going to be the D. Alright? But figuring out the R and S is a little tricky. So What's our new method? It's the stick figure method. So the stick figure method is essentially, you know, what's the clockwise counterclockwise rule? That rule is that the D has to be going away, right? And then you look at clockwise or counterclockwise. So what I just do is I draw a little stick figure on the opposite side of the carbon where the D is. So the stick figure's looking at the carbon, and they're like looking, dot 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 dot. They're looking, right? And what do they see? What do they see? You have to imagine you're the stick figure, and you're deciding, you're trying to figure out where's the ABCs? Where's the ABCs, right? So when I'm there, I'm looking at the carbon. I see something that looks like this, right? It's almost like a Newman, right? What does the person see? Straight down. Straight down is what? A, B, or C? Straight down from their position is the C. And the bromine is coming out at where we are, right? The bromine is over here somewhere. It's like towards us is where we are, right? Currently. So where does the stick figure see that B? Where the bromine is it on the left or the right? Imagine what they're seeing. What are they seeing? They're looking at the carbon, and then this wedge thing is out here in space. So is the B on the left or the right? Well, the BR is over here, like where we are looking. So it's right there. It's on the left. And then the iodine is into the page of the paper. So from the stick figure's perspective, the iodine must be to the right. Okay? So this is the stick figure method, and now we just do our clockwise counterclockwise thing, and we're like, oh well, is that clockwise or counterclockwise? That would be counterclockwise. So is it R or S? Counterclockwise is always S, so it's S. So what is the name? Let's ignore the stereochemistry and come up with a name, because this is we got to do that too, right? How many carbons do we got? What's the longest chain? It looks like 2 carbons, right? So it's ethane, right? It looks like it's going to be 1 bromo, 1 iodoethane. 1 bromo, because this is sometimes we did this a couple chapters ago, but you might have forgotten. We look at there's 2 substituents on this carbon. This would be carbon 1. That would be carbon 2, right? So it'd be 1 bromo, 1 iodoethane. 1 bromo, 1 iodoethane. Technically, you would combine the iodine with the ethane. You don't need a dash. If you put a dash, I don't really care. That's not a big deal. And now is it R or S? It's S. Okay, so that's the stick figure method. S, 1 bromo, 1 iodoethane. Okay? Keep doing a couple more examples as we get used to this whole thing. Let's try another example. And let me just mention one more time. When would you use the stick figure method? The time you'd use the stick figure method is usually when the D substituent, which is you have to envision going away. The stick figure method is if the D is in the plane of the paper, then you draw the stick figure on the opposite side of it, and you write what they see, okay? And then it's clockwise or counterclockwise. Counterclockwise S, clockwise R, all right? So this molecule, should we use the stick figure method, or the thumb method, or the H going away method? Well, the H is coming towards us, so I just think it's really easy to use the thumb method. I mean, I love the thumb method, so let's try the thumb method. Maybe let's draw the name without the stereochemistry first. So where's the numbering? I think it would be... I think we would go from, because we have to either number left to right or right to left. So in this case, the the numbering is going to be 1, 2, 3, 4, 5, 6, or it's going to be 1, 2, 3, 4, 5, 6. So there's a competition between, you know, why would we number from right to left or left to right? F will win alphabetically because F and M, you know, who wins alphabetically, F or M? Methyl or fluoro? It's going to be the F because it's lower in the alphabet. So it goes 1, 2, 3, 4, 5, 6. So it's going to be hexane. Now, what are the two things? We have a fluorine on F and a methyl on 2. So 2 fluoro, 5 methyl. 2 fluoro, 5 methyl hexane. 2 fluoro, 5 methyl hexane. All right. And what's the RNS now? We'll put in parentheses. RRS. All right. So let's get that now. Here's the A substituent. If we look at the periodic table, fluorine wins in terms of atomic number, A and D, and then either this piece with a bunch of carbons or the one carbon, who's going to be B? There's A and D, this is B and C. Alright, so D's coming towards us. I just love the thumb method. I poke my thumb towards myself, and I figure out, is it RRS? Okay, so I'm going to try my left hand. Left hand worked before, let's see if the left hand works this time. So I point my thumb kind of at myself, and then I wrap in the direction of A, B, and C. It's like A, C, B. Oh no, left hand didn't work this time. A, C, B does not work, right? Try the right hand. Point my thumb towards myself, and now it goes A, B, C. Ah, it's R. A, B, C. A, B, C. Thumb's got to go in the direction of the D substituent, which is coming towards us, so it's R. Alright, that's easy. Alright. Let's try another one. This is a scary one. Okay. So this got 2 chiral centers, right? It's got 2 chiral centers. It's got the bromine and the tert-butyl. Tert-butyl, right? Remember tert-butyl? And we have a dash, dash, dash. This is a pretty challenging problem, but we'll get through it. All right. 2 chiral centers. 2 chiral centers. You have the bromine and the tert-butyl, right? So if we first of all let's do the name without the chirality, and then we'll add in the chirality. Okay. So building the name, I usually start from the right side of the name. What's the size of the ring? It's cyclo something ane, right? 6-member cyclohexane. Cyclohexane, right? All right. And then the numbering. Is it going to be 1, 2, 3 or 1, 2, 3? Well, BR versus BU. Butyl, tert-butyl, right? Who is lower alphabetically? Because you have to rely on the alphabet here. BR versus BU. This is going to be lower, so it's going to be 1, 2, 3. Bromine, BR versus BU. BR is lower. Okay, so this is going to be 1, 2, 3. So let's do the rest of the name. It is 1 bromo, 3 tert-butyl. 1 bromo, 3 tert-butyl. Cyclohexane. The fact that I did that's irrelevant. Sometimes I stack those, like 1 bromo, 3 tert-butyl. Okay, so now what we need to do is we need to actually figure out the chirality on our 2 stereocenters. There's carbon 1 and carbon 3, so let's do them both. And it's going to be, the name then will be 1 something, comma 3 something. 1 something, is it, 1 will be RRS and 3 will be RNS, alright? A little scary. But this is getting closer to what you might see on a quiz, so we need to practice this, alright? It's going to be 1 something, 3 something. So let's first figure out 1. What I'm going to do is zoom in on 1. Alright, so 1 is RRS. Is it RRS? So here's my A, here's the BR, here's my D, is the H. I'm going to get rid of the 1, 2, 3 because that's not real. It's just going to get in the way. So once I have it, it's, you know, I know the Br is 1 and the tert-butyl is 3. Okay, so I have my A and my D. Here's my B and here's my C. Okay, so this is a odd situation. They're both carbons, right? We have A and D. Those are carbons and carbons. So now I walk away till my first point of difference. Right now there's no difference. So then I walk from that carbon or to that carbon, and now we're like, oh, the tert-butyl, that whole thing will make this B. So B is going to be here, and my C is going to be here. Okay? So we do one thing at a time. All right, now we have our A, B, C, and D. Very simply, D is going away, clockwise R. D is going away, right? Or it's A, B, C, it's clockwise, it's R. I can try my thumb into the paper also, and I see as R. Right hand, thumb in, A, B, C, R. A, B, C, A, B, C, right? Thumb in, A, B, C is R. So number 1 is R. I can just write that now. R. 1R. 3 is going to be what? Now I erase my previous work. Really recommend having a good eraser when you're doing this. Okay, erase your previous work, and now we have to focus on 3. Okay, who is the D substituent? Who is the D substituent? It's easy. By the H, right? D's the H. Where's the A substituent? Looking at this carbon, who would A be? It's, well, not that, it's not that. It's probably going to be the tert-butyl because it's got a carbon with 3 things on it, right? So this is A. Alright. So we have our A, we have our D. I always start with my A and I start with my D, right? Now we're like, who's B and who's C? Now you walk away till the first point of difference. You're like, okay, well, carbon, carbon, those are basically the same. So maybe it's going to be B here and C there. And the reason is because in the distance, you got that carbon with the bromine on it, and that's going to win, right? You walk away until the first point of difference. So that carbon and that carbon initially are identical. Then you're like, okay, well, walk further, and okay, now the carbon's got a Br, that's going to be B. But my A substituent, even though it's got the 3 methyls on it, my A substituent wins because as I looked immediately on that carbon, I saw 3 methyls. And the three methyls beat these guys which have a single carbon, right? So that's how I got my substituents, my A, B, C, and D. Okay? Alright, so is it R or S? Is it R or S? I love the thumb method here because the H is coming towards us. H is coming towards us. I point my thumb towards myself, and it's either going to be left hand or right hand, right? Point my thumb towards myself, and then wrap my fingers in the direction of A, B, and C. Let's try left hand first. And if I do that, it goes A, C, B, A, C, B, A, C, and wraps all the way around to B. A, C, B, right? Okay, so that doesn't work. Left hand does not work. Try my right hand now. Point the thumb in my direction, and then I have to kind of angle myself a little bit, and I'm like, okay, it goes A, and then it goes all the way around to B, no, it goes all the way around to C. It's a little hard to see. A, wrap around to B, wrap around all the way around to C. There's other ways you could do it. I could rotate myself a little bit and say, change my perspective or my position on my chair a little bit, and I'm like, okay, A, B, C, right hand R works. A, B, C, R. Okay. It's R. 1R, 3R. Okay. That's the final name. 1R, 3R, 1 bromo, 3 tert-butyl cyclohexane. 1R, 3R, 1 bromo, 3 tert-butyl cyclohexane. Okay? Alright. Cool. So, what else about this one? Let's try one more method for the 3. Because remember, the other thing you can do is just assume if it's, if H is coming towards us, you can just look at the clockwise, like it's clockwise, right? And if it's clockwise, normally that would be R. I'm sorry, normally it'd be S, right? I got my stuff backwards. ABC is actually counterclockwise, right? Normally counterclockwise would be S, right? Normally counterclockwise would be S. Normally counterclockwise would be S if the H was going away, but the H is coming towards us. So you could say, well, okay, ABC counterclockwise, but the H is going away. Not S, it's R. And you get the same answer. But the thumb method gets you there maybe a little bit easier. Okay? Alright. I'm going to show one other type of problem you might see, which is, say also, name to structure. Name to structure. Here we've been doing structure to name, right? Like draw a structure and you figure it out. What about name to structure? So what if I say, please draw 1s, 2s, 1 bromo, 2 chlorocycloheptane. Yeah, cycloheptane. 1s, 2s, 1 bromo, 2 chlorocycloheptane. How would you possibly do that? The answer is actually, well, what I do, you could either try to overinterpret this and be like, oh no, you know, 1s, 2s, like maybe try to draw the structure while you're interpreting 1s and 2s. I don't do that. What I do is I draw something, check it, and if it's wrong, fix it. So just draw something, right? 1 bromo 2 chloro cycloheptane. Start with that. 1 bromo 2 chloro cycloheptane. So I'm just going to draw that first. There's my cycloheptane, right? It's 7. 1, 2, 3, 4, 5, 6, 7. All right, the 7 member ring, right? And I'm just going to say, I'm going to ignore 1s and 2s. I'm going to ignore those. I'm just going to draw them randomly. 1 bromo 2 chloro would be, I'm just drawing this. And then I'm going to fix, and then I'm going to check it, and it might be wrong, and then I'm going to fix it, right? So this is carbon 1 on top, carbon 2 on the bottom, because you're using the alphabetization as your numbering, okay? 1 bromo 2 chloro. All right, so first I'm going to look at the bromine, and it's got to be S, right? They both got to be S. 1s and 2s, right? So let's see. There's the H. Is it S? That's your question. Is it S or is it R? If it's wrong, you fix it, right? Okay, so I see A, D, B, C. A, D, A, B, D, C. I see the D's going away, and it looks clockwise. A, B, C, D, right? Clockwise. Right? So did I draw that correctly? If it's clockwise, it wouldn't be S, it would be with D going away, right? Clockwise wouldn't be S, it would be R, right? Okay, so I know I messed up BR. So I'll redraw this, and I'll just flop the BR on the other side, and then everything will be fine. So right now I didn't draw 1S, I drew 1R. But I just used draw something and then fix it, right? So we know BR's messed up. Let's try chlorine now, right? Okay, let's check chlorine now. We just drew something. Let's see if it's wrong. So we know, I'll just put all X there. We're like, oh no, we messed up the bromine, right? So we'll fix that. But this is an H now, and this has got to be S also. So let's check if we did S or not. Okay, so this is the A, this is the D, this is the B, and that's the C. Okay, so we have A, B, C, and D. All right, the D is going away, so that's convenient. Now it looks like if I look at ABC, it looks like it's counterclockwise. Counterclockwise. ABC is counterclockwise. Is that S or R? Oh, it's S. Good. We actually want it to be S. So we made a lucky guess, right? We guessed S, and it is S. But the BR is wrong. So now what I do is I just redraw this and fix it. Oops. Okay. Okay, there's my ring, and which one was wrong? The BR was wrong. So now we just do, okay, BR CL. This is the correct answer. Okay? So what was my strategy for name to structure? If I give you a name, then just draw something that kind of, you know, has the chirality. Then you just double check what you did and then figure out what's wrong. And we figured out the BR was wrong, so we flipped the BR over. Now everything's right. So now this is actually 1s2s. You can double check it if you want. This should correspond to 1s2s. Okay. All right, so we're just going to stop now. This is a good introduction. I think we're on our way to you being experts at RNS, and this is called Ingold Prelog nomenclature. We definitely have some more cool stuff to do, and we're transitioning to more complicated structures. The main things that we've covered already, you know, what are the main things? Figuring out the priorities, which now you should be able to figure out the priorities. So figuring out the priorities, and then the other thing is once you got the priorities, figuring out which method you want to use to figure out RRS. Whether it's just H going away and clockwise R, counterclockwise S, or the thumb method, or some method to figure it out. You have a couple methods at your disposal. What's the third method? It was the stick figure method. And that's if H is going, or the D substituent is going in the plane of the paper. In that case, it's, you know, you just draw a little stick figure and then you see clockwise R, counterclockwise S. All right, see ya.